So how do we tell a good architecture from a bad architecture, or more specifically, how do we tell a good cache from a bad cache? Well, if you try to judge some kind of performance or judge a computer, if you go out to the store and ask the salesperson to tell you about, what's good about the computer, they most likely will tell you about the frequency they executing, or what number of cores you will have in that computer these days. But these numbers, actually frequency or number of cores, doesn't necessarily tell you much about how efficiently you will be able to use the computer yourself. In architecture, we typically measure architecture goodness by cycles per instructions. So that is how many cycles it takes to complete each instruction. So if you can complete an instruction every other cycle, CPI is 2. Or sometimes, just to confuse the enemy, we also talk about instructions per cycle, which is 1 over CPI. Or instructions per cycle, of course, tells how many, on average, how many instructions you can complete per cycle. And since we typically can have many parallel pipelines, as we saw in the crash course, and we can also have many cores on the chip, sometimes you can complete many more than one instruction per cycle. If you really would like to understand how good a computer performs, then you typically should run some kind of benchmarking. So spec floating point, spec int measures certain properties regarding floating point operations and integer operations. It's a selection of 20, 30 applications. Right now, you can have other benchmarks like TPC-C, TPC-D, which are database benchmarks, and so on. So there are lots of different benchmarks you can use to measure computer goodness. But as always, you need to have a representative set of benchmark if you're going to judge a computer. So you judge it for exactly the kind of problems that it's going to be used for later. Here we're going to talk about the goodness of a cache implementation itself. So we're going to look at a specific ways of measuring that. In order for us to tell if a cache implementation is good or bad, you may want to know its hit ratio. So what is the likelihood that a accessed piece of data actually is in the cache? Its miss ratio, which is 1 minus hit ratio. So what's the likelihood that you will not find the data you're looking for? How many cycles does it have to access the data if you find it in the cache? What's the penalty if you don't find it in the cache, the miss time? What fraction of instructions is accessing memory, so the memory ratio, and so on. So lots of different parameters. Right here, we're going to focus on the first 5 parameters. So if we know the cache hit ratio, hit time, miss latency, and memory ratio, we can compute for this a specific architecture the cycles per instructions or instructions per cycle that architecture will give us. So let's make an assumption here. So let's assume that we have an infinite bandwidth to and from our caches, to and from our memory, so that's not going to be a problem. Let's assume for now that we have a perfect CPU or perfect core that when it's not accessing memory is executing exactly 1.0 cycles per instruction and 1.0 instructions per cycle. And let's assume that 100% of the instructions hit in a specific cache where we store the instructions called instruction cache. So everything is perfect apart from the cache that stores the data. So then if we know the memory ratio, if we know the average memory access time, then we can calculate the total number of cycles that it takes to execute a specific program by multiplying the number of instructions by the average access time per instruction. And the average access time per instruction is 1 minus memory ratio. So these are the fraction of instructions that do not access memory, and they, by definition, take 1 cycle, plus memory ratio, the fraction of the instructions touching memory, times the average memory access time. Okay, and then the average memory access time we can calculate if we know the hit ratio. So we take hit ratio times the hit time plus miss ratio, so that's 1 minus hit ratio, times the miss time. So if we have the memory ratio and we have the hit ratio and we have the hit time and miss time, we can now calculate how many cycles it takes to execute that specific program. And of course, the number of cycles, we divide that by the number of instructions, and then we get CPI. So the CPI for this very simplistic architecture has the components, this component here, which is the non-memory instructions, and then we have this line here, which are the memory instructions that hit in the cache, and this line here are instructions that miss in the cache. It's, the very third grade math, quite simple. So here you have that in equation again. And if we now plug in some kind of realistic number, so the cache we designed in the previous video, we may have a hit ratio of 85%. It's typical that 1 instruction out of 4 is a memory instruction. So its memory ratio of 25% is quite common. Hit time to cache in this example we say is 3 cycles, and the time it takes to access the data if we miss in the cache is 100 cycles. So we just plug in the numbers here, and we can get the CPI for this perfect core running with this simplistic cache design. So we have the green component, we have the blue component, and we have the red component. And it all comes together to 5.14. So that means that even though we have a perfect core that, if everything is ideal, can complete an instruction every cycle, this cache will slow down the execution by a factor of 5 or more. That's because the memory is slow and we are not getting a perfect hit ratio in that cache. Here we have the same equation, we have the same input numbers, and that was the equation here that gave us the 5.14 in CPI. Now we can ask us a couple of questions here. First of all, are we satisfied with this? We have a computer that's capable of starting a new instruction every cycle, and we're just getting 1/5 out of its performance. And we clearly need to improve the cache design. So how can we do that? Well, one way to do that would be to buy twice as fast CPU while everything else stayed the same. So we can clock that at twice the frequency, but measured in nanoseconds, the cache is not any faster and the memory is not any faster. So twice fast CPU, that will change the CPU component of this, instructions that don't access memory. So it's a minor improvement. We could buy ourselves faster memory. It's already 100 cycles for an access time to memory is quite fast. But let's say you can buy even faster memory. Would that improve our performance? Well, a little bit. It's still a little bit over 4 on the CPI. And the way you really can make this this architecture improve is actually don't bother to improve the CPU, don't bother to buy faster memory, just improve the hit ratio. So if you make that 95%, that means that the second and the third component here changes, and the net effect is a CPI of below 3. So this is just a simple math equation that should motivate you why it is incredibly important to make sure that you have applications that perform well with caches, and to make caches that will explore the locality of those applications and make the hit ratio higher. So how do you get more effective caches? There are lots and lots of things we're going to talk about during this course. One is, of course, that you make the cache larger, so more capacity. You can use larger block sizes or something called cache lines. You can make more placement choices. Instead of just having one telephone number per page, you can increase what's called the associativity. With more placement choices, the cache is going to perform better. You can have lots of innovative caches. So we're going to talk about victim caches and skewed caches and so on. You have cache hierarchies with small caches close to the processor and larger caches further away from it. You can use latency hiding techniques, and we're going to talk about that in conjunction with when we discuss memory models. You can do latency avoiding, so there's something called prefetching that you can use either hardware or software. You can sometimes do cache avoiding. Sometimes it's better not to put the data that you read from memory into your cache. So you can do something called cache bypassing. And you can optimize applications and compilers. So that's in a few videos. But when we try to do all these things, when we try to improve the caches, we have to be able to communicate with each other and talk about what property has been improved, either by changing the application or a property has been improved by changing the cache implementation itself. So why do you miss in cache? And this is a very important slide here. So my good old friend Mark Hill from University of Wisconsin once wrote a paper where he said that in a uniform architecture with just one CPU, there are just 3 different reasons for why you miss in a cache. One is that you touch a piece of data for the very first time. Okay, so okay, you touch the data for the first time, it's not in the cache. Well, that's easy to understand. So it's a compulsory miss. So in Swedish, this compulsory is obligatorisk. It could be a capacity miss. And you miss in the cache because you are touching more data than there is space in the cache. So when you go back and touch the same data for the second time, it's been thrown out of the cache. It's too small, for crying out loud. And there could be a conflict miss. So that means that it's not a compulsory miss. You have touched this data once before. It's not a capacity miss. The cache is larger than the entire data set you're touching, but you miss anyhow. And that's because it's a non-ideal cache implementation. Clearly, for all of these kinds of misses, there are different ways we could redesign the cache to make sure that we avoid them. The reason I say this slide is important is we need to be able to communicate with each other. We need to understand when we have a new cache design what property that it improves, which kind of misses will be removed because we made a specific change to the cache. When we talk about multiprocessors later on, we will also talk about more kind of misses that can occur in a multi-core or multiprocessor implementation, but more about that later. So here's a question. If you think about the telephone book example or the address book example, and you try to find the telephone number of a new friend in your address book, what kind of cache miss corresponds to the fact that you can't find this friend in the address book? Now, if you have so many friends that you just can't keep them all in the address book, and you simply have more friends than there are pages, or than there is, than you can possibly store in all the lines of the address book. So that's why you miss in the cache. What kind of miss corresponds to that? That kind of cache miss corresponds to that. And finally, you don't have enough space on the age page in the address book. So even though you have very few friends, you still keep missing in that address book. So what kind of miss does that correspond to?